welcome to the course Excelling with Mathematical Modeling. In my previous lecture, we were talking about the discrete models and the tools that we will be using to solve those discrete models, mainly the difference equation. In this lecture, we continue with this. So, the next difference equation that we will be solving is un equal to a times un minus 1 plus b. If you recall, we have already solved the differential equation of the difference equation of the form un equal to k times un minus 1, and we have shown that the general solution is un equal to c times k to the power n, where this c is arbitrary constant. Now, we have the same form, but only now we have a constant b. Let us see what is the solution of this particular difference equation. So, if you write this un, which is a un minus 1 plus b. So, what I am going to do is I will be replacing this by un minus 1 from here. So, if I write un minus 1 and I use the same difference equation, I will get this is a times un minus 2 plus b. Similarly, if I write un minus 2, this is a times un minus 3 plus b. So, the first step is I will replace this un minus 1 by this particular difference equation, and I get a times un minus 2 plus b equal to a square un minus 2 plus ab plus b. So, this I can write as b taken common a plus 1. Now, in the next step, I will replace this un minus 2 by this, and you will get this is a times un minus 3 plus b times a plus 1. This can be written as a cube un minus 3 plus a square b plus b into a plus 1, and I take b common. This is a cube un minus 3 plus b common a square plus a plus 1. Now, if we continue this, you can clearly see that if this is 3, this is n minus 3, and this is 1 less. So, if this is 4, this is going to be n minus 4, and this is 1 less, which is it will be 3. Now, if it is n, so I will write as u times n minus n, which is u0, plus b times this will be 1 less. So, a to the power n minus 1 plus a to the power n minus 2 and a square plus a plus 1. Now, this is a known series, it is a GP series, and if I want to find the sum of this, it is a to the power n minus 1 by a minus 1, provided your a is greater than 1, and this is equal to a to the power n u0 plus b times 1 minus a to the power n by 1 minus a when your a is less than 1. And if your a is equal to 1, then you just directly substitute it here. So, it is u0 plus, so 1, 2, 3 till n times of these numbers. So, it is n times b, and this is a equal to 1. So, again you have to remember these two form of difference equation. One is this and another is this. Most of the discrete models that we will be doing will have a formation of this kind of difference equation, and if you remember the solution, you can quickly write them and go for further analysis. Otherwise, you have to solve them in this methods that has been shown here. The next difference equation that we will be solving is second order homogeneous linear difference equations. So, which is of the form a0 u to the power n plus a1 un minus 1 plus a2 un minus 2 equal to 0. Now, to solve this, we assume that let un equal to c k to the power n, where c not equal to 0, be a solution of 1. So, this is your equation 1. So, you substitute it here and you will get a0 c k to the power n plus a1 c k to the power n minus 1 plus a2 c k to the power n minus 2 equal to 0. If I take c k to the power n minus 2 common, I will get a0 k square plus a1 k plus a2 equal to 0. Now, this is not equal to 0 and the only thing that is equal to 0 is this equation. So, a0 k square plus a1 k plus a2 is equal to 0. This is called the auxiliary equation. And you have to solve this auxiliary equation to get the roots of this equation. It's just a quadratic equation, you can use any formula. So, you can use that k equal to minus b plus minus root of b square minus 4 ac and divided by 2a. So, let the roots be m1 and m2. So, now we take the following cases. Your case 1. Say m1 and m2 are real and distinct. Then the solution will be, the general solution will be of the form C1 m1 to the power m plus C2 m2 to the power m, where your C1 and C2 are arbitrary constants. Your case 2, where m1 and m2 are real and equal. Here it was real and distinct, means unequal, here it is real and equal. Then your general solution is given by C1 plus C2n m to the power n, where again this C1 and C2 are arbitrary constants. And finally, the case 3, where roots are imaginary. And since it is a quadratic equation, it will have 2 roots, and if the roots are imaginary, they will appear in conjugate pairs. So, your m1 has to be some alpha plus I beta, and your m2 has to be in the alpha minus I beta conjugate pairs. So, the solution will be of the form C1 m1 to the power n, where your m1 is alpha plus I beta to the power n plus C2 alpha minus I beta to the power n. But we put it in a more simplified form. We put alpha equal to r cos theta and beta equal to r sin theta. If you substitute it here, you will get C1 r to the power n cos theta plus I sin theta whole to the power n plus C2 r to the power n cos theta minus I sin theta whole to the power n. Now, we use De Moivre's theorem, and we know that cos theta plus I sin theta will be given by cos n theta plus I sin n theta. Similarly, C2 r to the power n cos n theta minus I sine n theta. So, if I take r to the power n common, inside will be C1 plus C2 cos n theta plus I C1 minus I C2 some sine n theta. So, I replace this whole thing by another constant, say some A1 cos n theta plus some A2 sine n theta, where this r is given by, so if I just square them, r square is alpha square plus beta square. So, r is going to square root of r square plus beta square, and tan theta is equal to beta by alpha. So, your theta is equal to tan inverse beta by alpha. So, you can get what is theta and what is r. So, you have to remember this derivation is not required for the for remembrance, it is for the sake of understanding that how you are getting this formula. So, you can straight away remember the general solution will be of the form r to the power n C1 cos n theta plus C2 sin n theta. Obviously, this C1 and this C2 is different from this C1. So, I just replace this A1 and A2 by C1, C2. So, that is easy to remember the formula. We now take an example where we solve the equation u n plus 2 minus u n plus 1 minus 6 u n equal to 0, and the initial conditions given as u0 equal to 3 and u1 equal to 4. We have to solve this homogeneous difference equation. So, we take let un equal to c k to the power n, c not equal to 0, be a solution of 1. So, you substitute it here. So, un plus 2 will be c k n plus 2 minus c k n plus 1 minus 6 c k n equal to 0. You take c k to the power n common. So, k square minus k minus 6 equal to 0. So, clearly c not equal to 0, and there is no value of n for which k to the power n not equal to, can be equal to 0. So, this implies k square minus k minus 6 equal to 0. We quickly factorize it. So, this is k and this gives me k minus 3 into k minus 3 equal to 0. So, k minus 3 k plus 2 equal to 0, and the value of k is 3 and minus 2. So, the roots are real and distinct, and this implies general solution is un equal to some constant minus 2 to the power n plus b 3 to the power n, where a and b are arbitrary constants. Now, these two conditions are given, which we have to use to find the values of a and b. So, you have un equal to a minus 2 to the power n plus b 3 to the power n. You have u0 equal to 3, which implies a minus 2 to the power 0 plus b 3 to the power 0 equal to 3, and gives a plus b equal to 3. So you get one equation, say number 2. And you have u1 equal to 4. This implies a minus 2 to the power 1 plus b 3 to the power 1, which is equal to 4. And this is minus 2a plus 3b equal to 4. This is equation 3. So we multiply this equation by 2 and this equation by 1 and add them. So we get 2a plus 2b equal to 3 minus 2a plus 3b, sorry, this is 6, and minus 2a plus 3b equal to 4. If you add, so this is 5b equal to 10 implies b equal to 2. And if you substitute here a plus b equal to 3, this gives a equal to 3 minus b, which is 1. So the value of a is 1 and the value of b is 2, and you substitute it here and you get your required solution as un equal to minus 2 to the power n plus 2 into 3 to the power n. So that is how you solve this difference equation. Let's move on to another example. Say un plus 2 plus 4 un plus 1 plus 4 un equal to 0, and you have u0 equal to 2, u1 equal to minus 6. So just as before, you write let un equal to some ck to the power n with c not equal to 0 be a solution of 1. So you substitute this here and you get ck to the power n plus 2 plus 4c k to the power n plus 1 plus 4c k to the power n equal to 0. Take c k to the power n common, k square plus 4k plus 4 equal to 0. So clearly c not equal to 0, and there is no value of n for which k to the power n can be equal to 0. So this will mean k square plus 4k plus 4 equal to 0. And this implies k plus 2 whole square equal to 0, and we have a repeated root. So if you have a repeated root, then the general solution is given by un equal to a plus bn into minus 2 to the power n. And this is because the roots are real and equal. Now, you have been given two conditions which you have to substitute here and get the value of the arbitrary constants a and b. So I write this one again, un equal to a plus bn into minus 2 whole to the power n. So you are given u0 equal to 2. This will imply a plus b into 0 into minus 2 to the power 0 equal to 2, and this clearly implies a equal to 2. and u1 equal to minus 6, and this implies a plus b into 1 into minus 2 to the power 1 equal to minus 6. This implies a plus b equal to 3. This implies b equal to 3 minus a, it is 3 minus 2 equal to 1. So, the value of b is 1. So, a is 2, b is 1, we substitute both of them here and you get the required solution. As un, a is 2, b is 1 minus 2 to the power n. So, suppose you were asked to find un. If your u0 is equal to 0, your u1 equal to 1 and your equation is un plus 2 plus 16 un equal to 0. So, as usual you take the solution to be of the form c times k to the power n, where c not equal to 0, and you substitute this in equation 1. So, you will get c times k to the power n plus 2 plus 16 times k to the power n equal to 0. This will give k square plus 16 equal to 0, as c is not equal to 0, and this will give your k is equal to plus minus 4 times I, because you can write this as k square is equal to minus 16 equal to 16I square. So, once you get it, you have the solution. The solution was, here you have two roots, however, their real part is 0, but if I write that formula, you will get it in the form C1 r to the power n, C1 cos n theta plus C2 sin n theta. So, if I substitute it here, so your alpha plus I beta is equal to 4 and alpha minus I beta is equal to 4 I, this is minus 4 I. So, you can see that your alpha becomes 0. So, your r, which is equal to square root of alpha square plus beta square, is just beta, which is 4. So, and your theta, so tan theta is equal to beta by alpha, and since alpha is 0, this becomes, so alpha tending to 0, this becomes infinite, and your theta will be pi by 2. So, if I now substitute it here, I will get 4 to the power n C1 cos n pi by 2 plus C2 sin n pi by 2. So, this is the general solution, but we have been given two conditions, that is u0 equal to 0 and u1 equal to 1. So, if we use this, so this is your un. So, u0, that is n is 0. So, if n becomes 0, then this value is, this is 1 C1, because cos 0 is 1, sin 0 is 0, and this value is 0, which implies your C1 is equal to 0, and your u1 is equal to 1. So, this implies I put n equal to 1 here. So, 4, already C1 is 0, C2 sin pi by 2, and that value is 1. So, this gives your C2 is equal to 1 by 4. So, if I substitute it, your solution will be of the form un is equal to 4 to the power n your C2 is 1 by 4. So, 1 by 4 sine n pi by 2. A little simplification, 4 to the power n minus 1 sine n pi by 2. So, the solution of this particular difference equation is un equal to 4 to the power n minus 1 sine n pi by 2. We next look into some graphs, some solutions, the visualization of solutions of some of a particular form of difference equation. So, you will see that solutions of homogeneous linear difference equation with constant coefficients. So, when we were discussing this, we have assumed that the constants, which is A0, A1, A2, they are all constant coefficients. So, they are a combination of the basic expression un equal to c times k to the power n. So, mostly your general solution will be of this form for the models that we will be doing in this course. Now, what will happen to the solution of this difference equation depending on this value of k? So, suppose k is greater than 1. So, if your k is greater than 1, you have this un equal to some c times k to the power n. You will get a solution like this. Now, what is the conclusion from this solution? Obviously, you put some arbitrary value of c or some conditions will be given from where you will get this value of c. And then you will plot this graph, and when you plot this graph, the dynamics will depend on the value of k. So, the case 1 is suppose k is greater than 1 and you get this kind of graph. So, it is clear that the solution becomes unbounded as n increases. Since this is a solution of a discrete equation, you can see that it is given 2, 4, 6, 8. So, it starts with 0, 1, 2, 3, 4, 5, 6 like that. So, if k is greater than 1, our conclusion is the solution becomes unbounded as your n increases. So, basically you have to remember these kind of dynamics. If your k lies between 0 and 1, so you can see it starts from some initial value and slowly decreases to 0. So, your k to the power n, because you have the solution un equal to c times k to the power n, it goes to 0 as n increases, and as such your un will also decrease and goes to 0. So, if your value of k lies between 0 and 1, you will get a curve like this, and the conclusion from the curve is as your n increases, your un decreases. The next case, if k lies between -1 and 0. So, as you can see, this is some sort of oscillation and a damping one. So, it starts with some large value and slowly it damps and goes to 0. So, your conclusion is k to the power n oscillates between positive and negative values with diminishing magnitude. So, as you can see that it starts from some higher value and slowly it goes down like this. This is a, so if it's a discrete one, I have to join like this and it goes some sort of damping oscillation. If k is less than -1, then you can see again it oscillates between the negative and positive value, but with increasing n the magnitude increases. So, in this case k to the power n oscillates between positive and negative values with increasing magnitude. So, the reason we are doing this 4 cases is that when you get the value of k lying between these ranges, you have to remember the curve so that you can easily draw the curve and you can conclude from that curve with respect to the model. Otherwise, you have to plot them using Microsoft Excel and get the same kind of curve. Now, some marginal points. So, what happens if your k is 1? You will get, because your solution was un equal to c times k to the power n. So, you will get un equal to some constant. If your k is equal to 0, you will get un equal to 0. And if your k is -1, then you will get, it is an oscillatory solution. It will oscillate between -c and +c. So, summing up, in the last 2 lectures, we have learned the basics of the differential equation, how to solve the difference equation and its graphical visualization. In the next lecture, we will be learning how to solve this difference equation with the help of Microsoft Excel. Till then, bye bye.